So this lecture is going to be shorter than the infrastructure lecture, but it's going to be kind of in the same style as an overview of what you might want to know about data management. So to remind ourselves of the landscape of all the tooling and infrastructure that we're looking at, data is over here, kind of foundational to everything else that's going to come after it. And before I delve into the actual details of like the tooling and advice for where to store what, I just want to kind of cover a basic, I think, philosophy of data. A lot of people think it's boring and kind of like. I just wanted to read some tweets from this blog post that's really good. One of the biggest failures I see in junior machine learning computer vision engineers, complete lack of interest in building data sets. It's boring work, but I think there's much to be learned in putting together a data set, and it's like half the problem. And that is definitely true in the field of computer vision. Like, the field pretty much alternates between publishing a new data set and then publishing a few papers that like beat the benchmark, and then publishing a new data set, and then that's been going for decades now. So as a computer vision graduate student, I have that instilled in me, which is like the data set really is like half or more of the problem. And so I've never shied away from the data. But a lot of people that I meet that don't have that kind of academic background, at least in computer vision, just don't expect the same thing, I guess. They don't want to spend time on data. Here's another one. A popular data scientist, Twitter person, Vicky, has said, okay, someone titled data scientist, or it could be machine learning engineer, I'm sure. I spend most, like 60% plus of my time on, and here's some choices, picking features, models, cleaning data, moving data, deploying models in production, analyzing, presenting data. So most people spend most of their time on cleaning data and moving it around. And here's one more. For the last few machine learning projects, the complexity hasn't been in the modeling or training. It's been in the input pre-processing. And I find myself running out of CPU more than GPU. And actually not, running out of like things that I know how to do because I now have to like process all this data in a complicated way. So what I want to talk about when it comes to data is that most deep learning applications just require a lot of labeled data. Unsupervised learning is something that's been on the horizon for a while now. But supervised learning is really the thing that works and is the workhorse of most companies and applications. There's things like reinforcement learning where you can just kind of play the same game or play yourself if you're training like a chess or Go player. And GANs, which generate synthetic images or something like it, where you're dueling another network. These things don't require a lot of labeled data, but they're also not yet practical for building a company around or bringing into your company as an AI project or getting a job as an ML engineer. If you just stick to using publicly available data sets, then that'll work, but you have no competitive advantage because I can come along and use the same data set and then add some of my own data and then probably be better than you, right? So really, the name of the game in deep learning is proprietary labeled data. That said, publicly available data sets can serve as a useful starting point. Like you can get something working on a publicly available data set, release it as a product with a good user experience or in a domain that it hasn't previously been applied in, and then rapidly gather data and scale up. So usually you spend a lot of money and a lot of time and you just label your own data. So this is something from, I'm actually not sure what company this is, deepsense.ai. Well, this is satellite data. Some of you guys are companies probably processing satellite or similar data. And it's just a lot of tedious labeling, right? You have to label every car, every building, trees, and whatever you care about, crops. And there's pretty much just no way around it. You just have to pay people to label data, which takes time. Now, an interesting thing that I like is the data flywheel, which is you can label a small data set or you can get something working on a smaller data set and then release it as a product and then ask your users to label data for you. And then very quickly you have a very large data set. So Google Photos is an example that I like to give, which if you guys have used it, it like finds faces, asks you for their names. I mean, that's optional. But then also every now and then it suggests, it like pops up a thing like this and says, are these two faces the same person? And then you let them know. And that's amazing because it's your photos, so you presumably care a lot about them, right? They're your friends or relatives or pets. And so you're probably not going to like give noisy data. So this is a great data source. And I'm sure Google's face data grew by orders of magnitude, after releasing Google Photos. Yep.
So this is something that I've been thinking about since we have a product where we put in AI in product that's customer facing. And one of the things that we've been thinking about a lot is, do we need to every data point that gets labeled by a user, does it need to be then validated by an internal expert or someone to be paid to validate it? Or can it be just accepted as is?
I think you usually want to quality control it anyway, using your own annotators. But for a product of this scale, I don't think Google has actual annotators looking at it. So what probably happens is, I'm not sure. It probably depends on the product. I would say for most products, they're not at this scale, and you actually could afford to hire enough annotators to look at what the user's saying. But the user usually gives you noisy data. I think this particular product is a good example of where the user probably won't give you noisy data because they actually want faces of their friends grouped correctly, and they probably take care in that. And it's too big to even hire your own annotators, so I don't think they really have a choice. But in most things, in something like this, if you ask your customer to let you know about mistakes, they almost certainly won't. Or if you ask them to annotate their own data, they'll probably not follow your guidelines and give you noisy data. So I think I'll get to annotators in just a bit. And then what I think is underrated is generating synthetic training data to get that basic version of a model, maybe to kick off even the flywheel. So here's a great example from Dropbox, a guy named Brad Newberg. It's a long, amazing write-up of exactly what they did to get. At some point, Dropbox started OCRing all documents that you upload into it, and it does it incredibly accurately. And so he describes everything that they did to get to that point. And the first thing, or actually a crucial part of it, was just generating a whole bunch of images of fake text, which makes sense because you have a bunch of fonts. We are able to generate image transformations that make it seem like it's a scanned image and stuff like that, rotate it. And pretty soon you can have a very large data set of fake data that's going to help you out. So it's not going to be enough to have a product in production, but it is enough to get the first version, I think, of the product in production, and then get that data flywheel going. Start, when the user knows that you're OCRing their documents, they'll start uploading more documents, which will, and maybe you give them a little opportunity to mark a document as incorrectly OCR'd. So very quickly you can get that kind of cycle where the user is sending you a lot of data for you to label that's valuable. So the roadmap that I want to get to is, so if we know we have to label data, how do we actually do that? What are some solutions for that? We always have to store the data that we get. So there's images, sound files, stuff like that, heavyweight files. Where do we store those? There's also stuff we usually call metadata, which usually lives in a database, which is just what's the name of your users, right? What are some tags they've applied to certain images and stuff like that. How do we version data? So once we start training on data, remember, machine learning models are part code, part data, and we version code with version control. But how do we version data? That's the question. And then as we ideally have that data flywheel thing, we are continually changing our data set, maybe improving the labels, adding more data. How do we make sure that every time we retrain, we can point to exactly the version of the data that we used? Data workflow. So workflow is this term that people use that refers to essentially a pipelining of data processing. I used to say data processing, but the term of art seems to be workflow management. And that's usually, you might have data on disparate systems, and it needs to go through different transformations until eventually it gets to a spot where it's actually trainable on. So it's called workflow. So to start with data labeling, I want to cover the user interfaces, the sources of labor for the interfaces, and potentially full service companies to do it. So data labeling is, sorry, I have, there we go. Most interfaces have like a standard set of features. You're able to draw a bounding box around some kind of part of the image. Maybe you're able to draw a polygon around the part of an image. That's called the segmentation. Or maybe for stuff like face annotations, you're able to annotate specific markers like tip of the nose, pupils, and stuff like that, key points. Or for three-dimensional data, sometimes you annotate cuboids. So that's a bounding box with a volume. And usually you have a set of applicable classes. So it's not enough to just say, like, there's something here. You want to be specific about what it is. And depending on what the application is, you may want to say it's a red car over here, or it's a Volkswagen over here. Whenever you have a labeling interface, training the annotators is really crucial. And so here's an example of like some examples that a researcher gave to the annotators of some image data set. So here's a fox. You're supposed to select all of the fox as tightly as possible, so as little background as possible, but all of the fox in the box. And if the fox is occluded, the human visual system is really good at just inferring where the fox is behind the occluder, but the computer vision system doesn't, depends on what you're trying to do, but usually it's just the head of the fox that should be labeled. So this particular example I'm giving as an example of, the boxes in red are totally reasonable annotations. But if you have all of these annotations in the same data set, you might have trouble training your model. So it's important to communicate to your annotators exactly how you expect your data to be annotated, or they will give you all this variety. And I think quality assurance is key, which is as your annotators are going through the data set, annotating, it's very helpful to either have other people check up on their work or have some kind of rankings of annotated quality, where if someone's provably very correct, every time you check them, they're perfect, then you can kind of stop checking them. And then some people, every time you check them, something is slightly off, so they have a low annotated quality. Where do you find these annotators? You really have, I would say, 3 choices. The first one is you just hire people, usually part-time. But if it's really the lifeblood of your company, then probably full-time. Usually you would outsource this. So you would hire people, not in the United States, or at least not in the Bay Area to do this. Yeah, Berkeley minimum wage is $15, which is very high for annotating data. But you hire actual people that have names and pay taxes. You promote the best ones to be kind of more in a quality control role because they've proved that they understand your standards. The pros of that are it's secure. So if you have secured, privacy concerns about the data, you don't want to just throw it up on Mechanical Turk. You potentially don't even want to get a contract with another company. Really, your only choice is to hire people, so it is very secure. It is fast because once you train them, it's the same people. They stay trained. They don't change from day to day. And less quality control needed because as they get better, they just get better. You don't have to control them as much. The cons are it's expensive because it's more expensive because you're paying. Mechanical Turk is a platform where people can go on and just do random tasks and get paid very little per task, but do a lot of different tasks. And then for you really want to be paying people by the hour. So it is a different economics. It's slow to scale. So if you all of a sudden need another data set annotated, it's hard to find people for that week to annotate and then fire them. Kind of sucks. And then there's admin overhead. You have to find the people, deal with the paperwork, deal with the quality control, chat with them. The other choice you have is crowdsource. So the standard choice for that is called Amazon Mechanical Turk, which is you throw up some human intelligence tasks on Mechanical Turk. Nameless hordes of people go and do your tasks. They're usually really bad at it. So you actually have the same task done like 3 times by 3 different people. And then you take the majority winner. Like if 2 of them agree, then you take that one. If none of them agree, you just throw it up again. So that's cheaper, even though you're doing the same task multiple times, because you're literally paying cents. Yeah.
Is there any way to automate sort of cross-annotator agreements for images? It's quite hard.
So automate as in, are there smarter things you can do than just take like best 2 of 3? Is that what you're saying?
Yeah, so imagine we have 3 annotators annotating the same object. How can we select the best one automatically?
Yeah, there are smarter things, and usually you don't want to be the one coding that smarter thing. So I think, let me just cover the cons of Mechanical Turk. So the cons are it's not secure at all, right? Shouldn't be putting private data on there. And significant quality control efforts required. So like, yeah, you got it labeled, but can you be sure that it's labeled accurately? How much work do you have to do to make sure that it's actually labeled? And then the last choice you have is hire a full-service data labeling company. And I think that's where those companies are highly incentivized to have labeling software as good as possible and processes that are as good as possible for that kind of stuff. And they spend time and money and research developing those solutions. I don't know of open source solutions that do anything smarter than essentially taking a majority vote on Mechanical Turk. Do you guys have any questions at this point? Yeah?
Yeah, so actually, I mean that for boundaries, it's hard to define what's the majority, right? So
I see, yeah. So specifically for images.
like overlap?
That's a good question. I don't have a great answer off the top of my head, but there are metrics for specifying how much an annotation agrees with another. So for a segmentation, it would be area of overlap over area of union. And you could just kind of eyeball some metrics that make sense and then make sure that, yeah, same thing. OK, so full service companies. So I think it actually makes sense to outsource data labeling because it really is a separate software stack. It's like a different user interface, not something you're going to ship to your users. It's temporary labor that you have to either hire or like crowdsource. And then quality assurance, which might actually require other user interfaces, require people or your time. So I think it makes sense to outsource. But the question is, how do you pick the company to outsource to, right? And I think the way to do it is to just dedicate several days to selecting the best one for your particular project. So I don't think there's a way around just labeling some gold standard data by yourself. And it's very good to get a sense of what the data set actually is, what kind of edge cases are in it. So you spend like a day just labeling as much data as you can yourself, trying to formulate what you're doing, and really signing off on the quality of it. Then I would just, there's different companies. I would take a sales call with several of them and then ask them to give you a work sample on that exact data that you already labeled yourself. And then just ensure that they're at least as accurate as you expect, like 90+% accurate, and then just take the cheapest one, I guess. So Figure 8 is kind of the original AI data labeling company. They used to be known as Crowdflower. And it's actually the same founders as Weights and Biases. So those guys are in the business of building tools around training models. But Figure 8 it's an enterprise software company. So as a startup, it's probably a little too hardcore. As a single person, it probably just doesn't make sense. I think it's like several tens of thousands of dollars setup cost, and then a pretty high annotation rate. But they have a lot of experience doing it. They have their own proprietary, software to do it. So, and their customers kind of speak to it, like Oracle and Tesco and SAP and stuff. Scale.ai has been kind of in the news, I think, as a dominant up-and-comer. And they essentially just do the same type of thing. You can do video, semantic segmentation, cuboids, polygons, 2D boxes, lines. And they give you like a nice little API. And the idea is almost like they're hiding the annotator labor from you. So like you just send them data, and it's kind of like you don't even know if it's their machine learning systems or actual people labeling your data. But the idea is that you're very happy with it. I'm sure their business model is to essentially get rid of human labor in their thing. So And then there's like a ton of others. So if you just search for data labeling companies, there's a bunch that come up. Labelbox seems to be pretty big. A lot of good users. Supervisely. And they all give you like an interface that's very similar. If you just go to a few, you'll see interfaces that are very similar. Data Turks is one we're actually going to use in lab tomorrow, in the most fun lab, where we annotate data. So, full service data labeling is going to be pricey because you're paying for their labor plus the setup cost plus the overhead. But some of these companies actually offer just their software without you having to use their labor. And that's kind of cool because you can hire your own annotators, but use their software to get the nice things about both the user interface and potentially quality control that they've developed. An example of that is, for example, Data Turks, or I think also Supervisely. And then there's some labeling software that's open source. In the computer vision community, like every research group had their own thing. But most recently, I think Prodigy is the one that people have been using the most that I've seen. And so Prodigy, what's that?
It's not open source, though.
Prodigy is not open source? Oh. Interesting. All right, well, I'm wrong on this slide. But the basic idea of this software, which is not open source, is that they use active learning to present to you data that is kind of most valuable to label. And the interface is nice and simple, and it kind of extends to different tasks, which both NLP tasks like part of speech and computer vision tasks like bounding boxes. So do you guys know of any good open source software for labeling?
So we used VOTT from Microsoft.
What's it called?
VOTT from Microsoft. It's pretty down. It's worked great for us.
Okay. What's that? Gotcha. Yeah. So my conclusions are you should outsource to a full service company if you can afford it. If not, then at least use someone's existing software so you don't have to write your own software stack. And then I think if you do have to hire for your own software, or sorry, if you are hiring your own labor, it makes sense to hire part-time than to crowdsource. Upwork is a great source of this kind of task. So I've had personally good experience hiring people, for example, in Texas, that turned out to be like amazing annotators for very cheap. And really spending time with them, training them up on the exact task, and they got pretty good very quickly. Next thing I want to cover is, you guys have any questions about data labeling? Yep.
So what do you think of all this approach taken by Magic Leap, where you basically have a 3D render from different angles, and then you have all the information about the picture and use that?
So I think the question is, what about other approaches to labeling data where potentially you just, instead of taking a single picture and then labeling the object in it, you take multiple pictures and then use computer vision to automatically label the object? Is that what you're saying?
Even more, you synthesize the picture yourself through 3D rendering.
I don't know. I don't have thoughts about that.
Like, basically, you have an image of, I don't know, a soda can.
Uh-huh.
You generate thousands of them,
Uh-huh.
like on the 3D render.
I see. So synthetic data for training.
Yes.
I think it's a great idea. Yeah. So I think that's what I was saying is an underrated trick, I think, is to generate a synthetic data set that looks very real. And it's an approach that a lot of self-driving car companies are taking, where like if you can learn to drive in a virtual world very well, then it's a smaller delta from a virtual world to the actual world than from nothing to an actual world. So I think synthetic data totally makes sense. And it doesn't even make sense to talk about labeling and synthetic data because you're generating data, so you know where everything is, right? Yeah?
How about anonymization? We've always found that
Oh, yeah.
you write special code to scrub out people's names and phone numbers and that type.
Yeah.
Other services, do you have to do it yourself?
I don't know if the services I provided do it. They probably do, or the agreement that you sign with them says that very confidential. There are things you can do to just scrub it out yourself. I don't know of any software that does it off the shelf.
The NML scrubber works great. It's released by the National Library of Medicine.
For what kind of data?
PHI. So phone numbers, addresses, names.
For text?
Yeah.
Okay. So, what's the name?
I'll put it in Slack.
Cool. So the next thing, yeah?
For synthetic data, what scenarios usually we need to generate? Because there are infinite scenarios, and I have this question that how I should choose the best one
I think
for training.
I need more context. Like for training a specific,
Like 3D pose estimation.
Uh-huh.
For example. You can generate millions.
how do you know which poses to generate?
Yes.
I think that's really highly dependent on the exact thing you're trying to do. I don't think there's a one size fits all, but probably just generate data that you're least certain about how to predict on. That's going to be the most valuable. So data storage, I want to talk about the building blocks of data storage, which are the file system, object storage layers on top of it, database, data lake, and then what goes where in a deep learning scenario. And then also where to learn more, which I think is important. So the file system is kind of like the foundational layer of storage. The fundamental unit is a file, could be text, could be binary, is not versioned, could be easily overridden. As simple as just locally mounting a hard drive, and it has all the files you need. That's potentially all you need as a file system. Could be networked. So if you have machines that are the same machines, you want to give them access to the same data, then you can set up a network file system on, across all of them so that multiple machines can access the same files without having to copy the files onto their actual physical drives. And lastly, it could be distributed, which gets into Hadoop distributed file system territory. And that's really not NFS. NFS is like it's stored somewhere, but other people have access to it. Distributed is it's stored on all of the machines. And so if you want access, you're going to have to ask the cluster where the file is, and it'll return it. So it gets a lot slower. The thing about file systems is just to be mindful of access patterns. They can be very fast, but they can't easily be parallel usually. So if you have the same file being accessed by a bunch of processes, they can't all read it necessarily. Object storage. So this is kind of what I think of an API over the file system. So you can get a file from the storage, put a file onto the storage, delete a file to a service, and without actually worrying about where it actually is or how it's actually stored. And the fundamental unit here is like an object. And usually this is binary. So you store images in Amazon S3. That's object storage. You don't know where they live. You just know that you're able to place an image, get an image, and delete an image. And the object storage interface takes care of the details. Now, because it's this interface, you can build cool things into it. So you can, for example, build in versioning into the interface. So you can just store files, and instead of overwriting files as you would on the file system, the object storage layer actually just makes a new version of that file. And then at some point, you can go back to the old version. And redundancy can be built into the service, right? So this can be very parallel, but it's usually not fast. And the reason I say it can be parallel is if you store a bunch of objects in S3, then it's actually across many different machines on the Amazon network. And many things can get that same file, and it's actually fetching them from all kinds of different places. But it's usually not fast because it goes through this interface. So S3 is the canonical example. Google, Azure has their own services here. And then for on-prem setup, there's a thing called Ceph, which people use. So the database is essentially persistent, fast, and scalable storage and retrieval of specifically structured data. So my mental model when it comes to databases is that everything is actually in RAM, so it's not even a file system, but there's cool software that ensures that everything is logged to disk. And so if the power is cut, you'll be able to restore everything. The reason I think the right mental model is that everything is in RAM is because the use of database really only makes sense if the lookups are fast, right? If the writes are fast, the lookups are fast, and if stuff is actually on disk and you're asking the database to like search around on disk or write to disk every single time, that's too slow. The fundamental unit is a row, which has like a unique ID, can reference other rows, potentially in other database tables, and then it has values in the columns. So the columns should not have binary data. You can store references to binary data. So the canonical example would be you have a database table of images that your users have uploaded, but it doesn't actually have the images. It just has the S3 URLs, or sorry, the S3 paths to where the images are actually stored. And usually this is for data that will be accessed again. So if you have a web server and you log when users log in and stuff, you're not going to write that stuff to the database because you don't actually need to very frequently look up when people log in, but you are going to log it somewhere where it's going to be in storage of a different kind. Postgres is the right choice like 90% of the time, and has like really good SQL. It has support for unstructured JSON, so you can actually get the benefits of NoSQL on Postgres, and it's like actively developed, releases every few months. So SQL is, I think, worth talking about. You guys are coming from different backgrounds. Some of you are from data science. Some of you are from just other software development. Some of you are from research. And eventually, like, we all interact with some SQL. And it is the right interface for structured data. I think the tendency of a lot of people who weren't taught that at some point is to fight it and like develop their own software, like pandas and stuff like that. But if you avoid using SQL, then you're just going to reinvent it. Like, it really is the right, like, everyone needs a declarative language for accessing large amounts of data, structured data. SQL is just the solution that we ended up with. We should all learn how to use it, because if we don't, we're just going to have to reinvent it. What is a data lake? I'm sure you guys have heard the term. So it means like an unstructured aggregation of data from multiple sources. So it could be from databases, it could be from logs, and then it could be outputs of certain data transformation that you do. And the basic idea is like schema on read. So database is schema on write. Like, you can't write data to a database unless it conforms to the row, to the table structure that it expects. But you can write to a data lake, and then when you read it, when you try to search the data lake for some data, that's when you essentially impose a schema on it. So this is kind of like a representation. You got multiple data sources. They all go into one place, just unprocessed. Then you can access them with some transforms and then package it up for different needs. So maybe you want to warehouse it for like business intelligence analytics, or maybe you want to package it up for TensorFlow training. Those are going to be two different processes doing the packaging, but they're both going to be accessing this kind of store of data. And on Amazon, the canonical solution is called Redshift. So what goes where in like a deep learning scenario? So binary data, like images, sound files, or maybe compressed natural language, should be stored as objects. So something like S3. Metadata, like how are your users interacting with your service, or how are the labels in your labeling interface, how should they be stored on the data? That should be stored in a database because it's structured and you're actually accessing it very frequently. If you need features that are like not obtainable from the database, like how many times did this given user log in over the last month, that's not going to necessarily be in the database, but it will be computable from entries in your log files. So for that, it's worth setting up some kind of data lake solution where you just dump all the logs and dump your database into the same place, so that later you can actually aggregate all the data you need. But then at training time, when you actually decided, all right, I need the number of times the user is logged in, I need these images, and I need the user's name from the database, at that point, you copy everything from all the sources onto the local file system or the network file system if you're going to be using multiple machines to access it. But basically, the idea is like if you're actually coming to use TensorFlow or PyTorch, the data should be local, like as local as possible, because it's very slow to read data from all these different sources. And when you're actually like sending stuff to the GPU, you don't want there to be any bottleneck between the data and the GPU. So does that make sense? You guys have any questions? Yeah.
How about in memory data stores like Redis and cache?
Yeah, so ideally, ideally at training time, everything is in memory. If you can't fit it in memory, it should be on the local file system. And if it can't fit in the local file system, network file system, distributed file system, and then to get files onto that is where you might end up using a data lake, which aggregates from other stuff. So there's a great book called Designing Data-Intensive Applications. Don't just hack it together. NoSQL, big data, CAP theorem. What does it all mean? How does it actually work? So it's dataintensive.net, recommend it. So the next thing I want to cover is how to version data. So I think of data versioning as like multiple levels of, complexity. Level 0 is just there is no versioning. That's where everyone starts out. Level 1 is you version it just by taking a snapshot. Level 2 is you version it in a better way that we'll talk about. Level 3 is you use some kind of specialized data versioning software. So level 0, you just got your data on your file system, or maybe in S3, maybe in your database. And you're not versioning on it. You're just kind of, I train on Tuesday. I'm using the data that's there on Tuesday. I train on Friday. I'm going to use the data that's there on Friday. The problem with that is that when you deploy the model that you train, that has got to be versioned. And the deployed machine learning model is part code, part data, right? If you're deploying something that's part code, part data, and it needs to be versioned, but the data is not versioned, then you can't really version the deployed model. And the problem that you will face is that at some point you'll want to revert, like you'll deploy a model and it'll mess everything up. You'll want to revert to the previous version, and you won't know how because you're not properly versioning the model. Does that make sense? So level 1 is you version the data just by taking a snapshot of it and then storing it somewhere. So on Tuesday I train, so I download all the data, I package it up, I store it somewhere else. On Friday I train, I download all the data, I store it somewhere else. And so then, I can actually deploy a model and it'll say, the code is this GitHub commit, git commit. The data is, Friday, March 2nd, 2019. And so then if something messes up, I'll be like, oh, shoot, I have to go back to February 24th, 2019. And I'm able to do that, but it's super hacky. So it'd be better if we could version data just as easily as we can code. So that's where I think we get to level 1, which is data is versioned as a mix of assets and code, which this is what it means for me. So let's say you're doing some kind of image processing or speech recognition. So your actual speech sound files or your images are stored in S3, but they have unique IDs, right? That's how you get them in and out of S3. So your actual training data is going to be a list of these IDs, and potentially with metadata like the labels, like what are they labeled with. You can check that JSON or whatever structured data format, you can check that into version control. And then when you check it out, you can go back to any point in time. As long as you never delete anything from S3, you can get back to whatever data you had at that time. So this is what I like. Now, JSON files can get big because you might have millions of examples. And so millions of rows in a text file is still going to be like several megabytes and probably not something you want to be checking into version control just like you do code. But there's a thing called Git LFS, which we actually use in the lab, which stands for Git Large File Storage. And this lets us store them just as easily as code. Now, there's a whole lab about versioning data tomorrow. So I'll be talking more about this tomorrow. So yeah, so then if you do this approach, then the version of the data set is uniquely defined by the Git signature of the code base and the raw data file, right? And then you know that the raw data file points to some larger objects that are stored in S3 somewhere. Yeah?
How future-proof this methodology would be? One of the risks that I see in our systems is the source data would change, like the IDs that are mapping into our actual data.
Yeah, that depends on, that's an interesting question. So the question is, how future-proof is this kind of scheme? Because, deployed systems are changing, right? So maybe we change the database schema, but then this thing is still pointing to the old database schema, or maybe we delete some data down the line. And I think the answer kind of depends on your actual application. So in my application, which is education, we are very strict about privacy. So we act like if someone tells us to delete data, we actually have to delete all the data. And that means I can't keep the data around to train on it in the future. So for my use case, this is actually a feature. Like, I want the data gone. I don't ever want to see it again if someone told me to delete it. But for some other applications, you don't have that constraint, right? Or you might have the opposite constraint. You really want to keep everything forever. So I think the right place to enforce it is kind of upstream of this, right? Where you might have contracts upstream that if you change the schema, some test breaks, and you get alerted to the fact that now your data thing isn't correctly stored. Or you have S3 with versioning enabled so that you actually never delete a file. You can only add a different version of a file. And then lastly, there's level 3, which is a specialized solution for versioning data. And I would just avoid these until you try level 2 and then can explain how level 3 will improve your life. But there's some names that I want to give you. So one of them is DVC, one of them is Pachyderm, and then one of them is Quill. So you can kind of do a little research into that, see if it makes sense to you. It hasn't made sense to me so far. But here's an example of DVC. It's an open source version control system for machine learning projects. This is the one that I find most exciting out of the ones I listed. It's kind of hard to see, but essentially you say, when you add a data file, instead of saying like git add data.xml, you say dvc add data.xml, and then that uploads the file to S3, and then creates another file called data.xml.dvc, which has that link to the S3. That's kind of what I was telling you guys to do here on level 2, but it just kind of does it automatically for you, which could be nice. And then let's say you want to transform that data.xml to something that you're ready to train on, which is going to be called data/test.tsv, right? So you record the transformation that goes from XML to TSV by saying dvc run, Python, transform data, whatever. And then DVC is able to kind of give you the pipeline at any time. So it like kind of maintains the pipeline of how the data was processed and the provenance of the data. I think it could be cool, but you guys should decide for yourselves. So the last thing I want to mention real brief is data workflows. So the motivational example that we'll have is like, let's say we have to train a photo popularity predictor every night. We have some kind of web service. And for each data, for each photo, the training data has to include the metadata, like where was this photo taken, when was it posted, what's the title of the photo. Maybe some features of the users, like how active is this user, how many times did they log in today. And then maybe outputs of some photo classifiers that we have that are just microservices running somewhere else on our system. So the metadata, like when was this posted, and the title is in the database. The features of the users we might have to compute from logs because we don't store that in the database, but it is in the logs. And then the outputs of the photo classifiers are actually not even run until we decide that we need them. And so we actually need to run the classifiers. So there's different tasks that we have to do in order to produce a trained model that predicts the photo popularity. So the fundamental idea here is task dependencies, like a directed acyclical graph of tasks. Like I can't start training my final model until I have all three of these things. And maybe I can't train my photo content classifier until I've extracted something from logs or something like that. So makefiles is probably where you've seen this in the software development context, where you say, OK, I need to compile this file, and in order to compile this file, I need these files. And then when I have these files, or when these files change, then run this command, and that'll generate this file. So that's nice. But what if the recomputation needs to depend on the content instead of the date, like in makefiles? What if the dependencies are actually not even files, but like different programs or databases? What if the work that we need to do has to actually touch multiple machines? And then what if there's actually 100 things that we have to run, and they all have to be running at the same time, and they have shared dependencies, right? So like you compute stuff from logs, and that's useful to many different tasks. So that's where this workflow stuff comes in. Luigi and Airflow are two Python-based solutions to this, which is why I bring them up. And there's other ones for Java, I'm sure, other ones for different languages. But Airflow lets you define this directed acyclical graph of tasks with Python code. So you can say, Python operator, this is the task ID. This is like the Python function that needs to happen. And then you might have a MySQL operator that like looks up something in the database and so on. And there's kind of two parts to this. One is the DAG graph specification. And that's done by writing code. But then the other is, OK, once we kick off a DAG, how do we actually distribute the work onto the resources that we have? And Airflow's solution is to not solve that, but to kind of outsource it to other things like RabbitMQ, which is a queuing system. So but the basic idea is that the workflow manager knows what it has to do and how to like go through the graph. It starts a queue for all the tasks. It starts putting stuff on the queue in the right order. And then it has a list of workers that start pulling from the queue. When they're done, they put the results back on the queue. If they fail, they just let the queue know. So that's kind of it, just in time. So do you guys have any questions about the last two things I covered? Because I didn't stop for questions before.
I did not understand what was S3.
S3, what does it stand for, or what is it?
Like
Yeah, Amazon S3 stands for, what does it stand for?
simple storage service.
Thank you. Simple storage servers. And what it is what I call, what is called object storage. So it's an abstraction of a file system where instead of saying like, I'm writing this file here, or I'm reading this file from here, you say, I would like to put this data at this ID path. And then later you'll say, I want to get data from this ID path. And then S3 manages where the data is actually stored. It actually stores it in many different places so that it's redundant. It can version it. So when you put a different version, it just automatically creates a different version. And it's just kind of like a nicer interface. And it also allows you to use the same data from many different machines, right? So you don't have to worry about where the data actually is. All you need to know it's on S3, and I can access it from anywhere. Yeah. Oh, yeah?
For Airflow and I guess Luigi, do you have recommendations on self-hosting managed solution?
I don't know of a managed solution to this, actually. What's it called? Oh, I see. That. I think my recommendation would be to at least try it yourself and then see if it makes sense to outsource it to another service. But yeah.
GCP recently added Cloud Composer, which is management.
Oh yeah, I guess I should say AWS has similar things. They're called step functions, I think, or batch functions. They're like two different things. But yeah, I think the cloud providers have versions of stuff like this. And perhaps I should have covered it, but I just covered the open source things that you can use on-premise or in the cloud.
I'm just curious, like, why didn't you use DVC? Because taking a very quick look at it, it looks not bad.
The reason I didn't immediately get super excited about DVC is because, well, actually, let me rephrase that. I did get immediately super excited about DVC. And then I looked into I started reading the docs. And they actually try to do a lot more than just this. So they really try to impose a workflow on you that I wasn't, didn't necessarily sync with my workflow at the time. So for example, like to kick off an experiment, they want you to commit a branch. But that's not necessarily the way I want to do things. And I like the foundational idea of like, when you add a data file, you shouldn't actually check the data file into version control. You should check in some metadata about the data file into version control. I totally buy that, and that's what we do in the labs. But this just seemed like a lot of too heavyweight and like too much workflow imposed on me for just that.
S3 is on the cloud, right? So every time you want to train something, you have to download all the data. What if my data is very large, right? What if you want something for my local?
So yeah, so caching. So let's say you train nightly. You train every night. and you maybe also update your data set every night. But your data set is not 100% different every night. Maybe it's 1% different. So like as your users upload stuff to S3 or whatever, every night, you already have the data you trained on yesterday on your local machine. And then you download the new stuff from S3, you add it to your local file system, you train, and then it's there for tomorrow. That's one way to do it. If you're training in the cloud, then you could be essentially packaging up data and then having like a large blob of data that you trained on yesterday stored somewhere else, or just on a volume that you can connect to a different instance tomorrow. So I think, yeah, the idea is caching, basically. All right, well, that's my time. Thanks for your attention.